I had to take a few slides out, and I had to take all of the backup slides out. So when you ask questions, I may just have to respond verbally. But let's get going. Okay, so 29 days ago, New Horizons completed the centerpiece of our first extended mission, which was the flyby of 2014 MU69, nicknamed Ultima Thule. I'm going to spend most of this presentation telling you about that flyby and what it took to succeed, and show you early scientific results. But before that, I have two slides that I think will be useful as preparation. So if we can go to the next slide. Yeah, I think probably everybody on SBAG, or most everybody on SBAG, remembers New Horizons as the first mission in the New Frontiers series at SMD. We launched in 2006, and in the summer of 2015 explored the binary planet Pluto and a system of satellites. If I can have the next slide. I just want to advertise that here we are going on, well, we are 3.5 years past the flyby now. Our team has published the better part of 100 papers, published or submitted the better part of 100 refereed papers, and giving many conference presentations. And we are now putting together a Space Science Series volume, which will be published in 2020. We have worked with Rick Benzel and his team, of course, at LPI, to put together a table of contents and invite lead authors and, in fact, co-authors as well. The conference that goes with that book will be the 14th to 18th of July. That does span a weekend, but it deconflicted with some other important planetary science meetings. Many of you may want to come to that. Abstracts will be due May 2nd. And there's already a website up at LPI, and there's a little bit of information here. And there was something in the PIN and the DPS e-newsletter just in the past week. So that's all I'm going to say about the Pluto system, but I did want to mention this important conference and book. Next slide. There we are. Okay. So as preface to the discussion of the flyby we just completed, the first flyby of a small Kuiper Belt object. This is our cartoon, more or less. This is our route of flight. As I said, we launched in 2006, intercepted the Pluto system in July of 2015, and are now flying across the Kuiper Belt until the late 2020s. Our current extended mission runs through FY21, so another 2 years and 9 months. Next slide. That extended mission was proposed after the successful flyby of Pluto. It's proposed to the Planetary Mission Senior Review, which we will go back to, I understand, next year as a New Frontiers Senior Review. But it received a very high score, the highest possible score, excellent. We were fully funded for this 5-year mission, which started October 1st, 2016. Next slide. Yeah, the extended mission has several parts. Most people think of it most famously for the close flyby of MU69, which we just completed. But in addition, we're using the spacecraft in 2 different ways as an observatory in the Kuiper Belt. One is that we're observing about 30 KBOs and centaurs across the 5 years in ways that cannot be achieved from any other facility. Either we're closer to them to give us a higher spatial resolution, looking for satellites on tight orbits, for example, that you can't do from the ground or with Hubble. Or we're observing from geometries that can't be seen from down in the inner solar system to get extended phase curves, and doing analogous things like that. Essentially to develop context information on small KBOs relative to MU69, and to develop a database of a few dozen objects for which we have complete phase curves, small body light curves that can't be achieved from Earth. We're looking at some dwarf planets also for their phase curves, but this talk is going to be primarily about the MU69 flyby, I just want to point out one other thing, and that is that almost 24/7 the spacecraft is using its two plasma spectrometers and the dust impact detector to make a transect of the Kuiper Belt to 50 AU, where we will be in 2021, to understand the space weathering environment and for some other objectives. And I think with that, we can go to the next slide. Yeah. Okay, so 2014 MU69 was discovered by our team using the Hubble Space Telescope in 2014. We actually found a small handful of reachable targets with that Hubble program. We selected 2014 MU69 because, number one, scientifically, it's a cold classical, and the cold classical Kuiper Belt objects are understood to be sort of a bedrock sample of the Kuiper Belt and the solar nebula that was actually formed in situ and not transported outward as many other Kuiper Belt populations are. So this is a truly primordial accretion product of the ancient solar nebula at about 44 AU, where it orbits. Secondly, this particular one of the cold classicals that we could reach required the least amount of fuel and gave us the earliest arrival time, which maximally lowered our risks and left us with the most propellant to entertain future extended missions. You see in that cartoon that we made a number of trajectory corrections. The actual targeting maneuvers were made in October and November of 2015, just a few months after the Pluto flyby. And then as we continued to refine our understanding of MU69's orbit in a number of ways, primarily with the Hubble, but also with ground-based stellar occultations, we made trajectory corrections to improve the intercept. And I think I can go to the next slide. Great. Okay, as I said before, MU69 has the nickname Ultima Thule. It is the most distant and most primitive object ever explored, and very briefly, our scientific objectives were to geologically map the target, both panchromatically and in color, as well as to observe it at a variety of phase angles and to obtain stereo coverage so that we can put together the topographic profile across the surface. We have a composition mapping spectrometer, which we also use to resolve hundreds of locations on the surface in the infrared from about 1.25 to 2.5 microns at a resolution of a couple hundred. And although we didn't expect an atmosphere, and as I'll tell you later, we didn't find one, we felt from a due diligence standpoint we should search. We have an ultraviolet spectrometer that we have used for that purpose, and we search for satellites and rings. And with that, I'll go to the next slide. Our knowledge of MU69 is pretty meager before the flyby. It essentially boiled down to knowing its orbit, which is presented there in the upper right, to understanding it's a cold classical, to knowing that its size is about 30 kilometers, and its color, as determined by the Hubble, is somewhat redder than Pluto. And other than that, and the fact that it had no large obvious satellites, we really didn't know anything about it. We tried to get its light curve from Hubble. We were not able to. It just wasn't showing a light curve within the signal to noise. We tried that on approach with our own cameras and actually never found the light curve, but we found the explanation for that, and I'll show it to you. Next slide. I do want to just point to the stellar occultations because they are very important. I know Mark Buoy is going to speak later at some length just about this capability. It's an amazing capability that Mark, who is a co-I in this mission, and his team have put together to be able to fuse Gaia data for the stellar reference frame background with accurate orbit determinations of KBOs and other small bodies to really push the state-of-the-art for occultation prediction to a whole new level. In this case, we were trying to get in the shadow of an object only a few tens of kilometers across, seen from 4 billion miles at 6 billion kilometers away. So Mark could tell you if that's micro arc seconds or tiny fractions of a micro arc second, but it's really state-of-the-art. We had 3 occultation opportunities in 2017 and 1 in 2018. They were at various locations around the world. The basic scorecard is that we got 3 of the 4. And most notably, we had success in July of 2017 on our third attempt, the second one that made a detection, in which we actually got multiple chords across the object and were able to determine not only its location in a way that really improved our orbit fits, but also to get a very good understanding of its size and therefore its albedo, which helped us with mission planning for target integration times. And also, it painted out the shape. And we can go to the next slide and I'll show you that. Take a look. As soon as I see it, there you go. There's Mark. The 5 means that we got 5 occultation light curves. To the right of Mark are all the occultation light curves from 2017. Both those that missed the target because we put broad fence lines out to try and snare it, as well as those that did detect it. And you see there in the middle the potato shape that the occultation profile actually revealed. Mark can show it to you, I think, in more detail in his presentation. But this was extremely important for us. I can't say enough about how important it was for us to be able to properly target MU69 for the flyby, to have a second independent astrometric data set and one of very high accuracy from the occultations. But additionally, being able to determine, as we could not determine whether it was a contact binary or a closely orbiting binary seen in projection. But this new capability, it turns out it's a contact binary, this new capability is going to be very important, I think, in the future for planetary science, to be able to do things with small bodies at a resolution that we never before could. And we can talk about that in the Q&A, but I'm going to press on. So next slide. Yeah, I just want to point out that the Ultima Thule flyby was a lot more challenging than Pluto. Navigation to a tiny target made optical navigation much tougher. The diameter is about 80 times smaller than Pluto, so the target's 80 squared times fainter, and right at the almost the limiting capability of our system to acquire it in the summer time frame when we did. We had an unknown hazard environment, lower lighting levels, which meant that we had to work harder to get the signal to noise. Longer communications times, up to 12-hour round-trip flight times now, which makes the mission operations more complex. And because we're an RTG-powered mission, and the RTG has a half-life, every year the RTG produces less power. And so we had to manage power in terms of instrument and avionics switching much more carefully than at Pluto. I should point out we have the power to operate for another 15 years at least, and we can do future flybys if we find targets. We just have to pay more and more attention to the power switching. Anyway, it was high stakes, no second chances, and if I can have the next slide, which may be in part 2, that may be where we split it. No, okay, a little bit more here. Take a look at the blue box that's outlined there. These are the best resolutions in meters per pixel that we designed to achieve. You can see for panchromatic imaging about 30 meters per pixel. Other data sets at different phase angles with other resolutions. I want to point out the best color imaging resolution that we expect from the flyby is about 500 meters per pixel, and that we will have kilometer per pixel composition mapping, which for an object that's 30 by 10 kilometers gives us quite a number of pixels on the surface. So this is a kind of exploration of a Kuiper belt object that was never before possible. There's nothing foreseen in terms of ground base that can give us this capability. We did fly quite a bit closer to MU69 than we did to Pluto because we didn't have to balance objectives with a complex satellite system like Pluto has. And we were able to certify that the path was safe to go for the optimal flyby distance, what we call the prime, at 3,500 kilometers from the target. That's the design distance. We actually hit that to within about 1%. So we're very happy with the way that turned out. And we conducted very many observations on approach and about a dozen very close approach observations. As far as we can tell, absolutely everything was successful. For example, the solid state memories filled up to very close to what we had predicted. And every observation that we've got on the ground has so far been very well centered and properly executed. Let's go on. There must be a break between the two sections. Okay, now this one, I don't know if it will work. It's actually an animated GIF, and you have to move the cursor down and get it to show you a start button, and then it will repeat itself over and over. It looks like you're going to be able to make it work. And if you do make it work, which I see you have, you can see MU69 appearing from the center of the field and over a period of several weeks, growing in brightness and accelerating in angular terms. These are all optical navigation images that were used for trajectory correction purposes. We actually made 3 trajectory corrections on approach using these optical navigation images. This is really another state-of-the-art feat or coup, if I can brag a little bit, for our mission, because we started with the first acquisitions of the target at 21st magnitude at a distance of greater than 1 astronomical unit. And for something lit so dimly as the sunlight is at 44 AU and with a low albedo and a very small cross-section, this really is beyond what has been done before. Next slide. You can go ahead. Whatever's next. Yeah, okay, so it was quite a success, like at Pluto, despite the fact that the federal government was in partial shutdown. We had about 100 media at the flyby, which occurred on New Year's Eve and New Year's Day. A lot of web impact. NASA TV managed to stay open because it was forward funded and staffed by contractors. We thank Administrator Bridenstine, who personally made that happen. We got a big bounce, I think, for the agency in terms of understanding of planetary exploration in the Kuiper Belt, small bodies. Next slide. I just want to show you a couple of behind-the-scenes views. This is an image in our geology and geophysics room at the Applied Physics Lab at the very moment that the first good resolution image of Ultima Thule was projected up on the screens, and I think you can tell there was a lot of emotion in the room, perfectly centered in the frame, but also just a spectacular object, as I will show you in a few slides. We can go on to the next slide, and I just want to also show this one because this just shows, I think this is in the same room, but at another time, how much work people had put into making this all come together, and it did come together perfectly. And we think we know how to do more of these if we can find an additional target. Next slide. Okay, the first resolved image of MU69 was transmitted to the ground just before the flyby closest approach on New Year's Eve. We called it a bowling pin. It very much reminded us of the shape that Bowie's Occultation team had painted out in silhouette. But even from this image, we really couldn't determine whether the two objects were separated or not, but it was clear that the Occultation had really nailed it. There you see it with a scale bar, 33 kilometers for the major axis. If we can go to the next slide, which is an image made just or sent to the ground the very next day, we quit calling it the bowling pin and started calling it the snowman. And this is just a spectacular image. For the first time now in planetary science, we really see a primordial contact binary that's unambiguously the result of the way the object formed and not, for example, due to its evolution in the inner solar system, as you might expect from comets. Also, I should point out, reminding you of that 21 mile and 33 kilometer scale bar, that this is a very much larger object than a typical comet nucleus of a few kilometers that we see. But looking at this image, we could not only tell that this is a contact binary, but there's a very interesting interface region between where the two lobes, which we nicknamed Ultima and Thule, Ultima being the larger of the two lobes. It's a very interesting interface at the neck between those two. We have much better imagery on the ground, which I will show you in this presentation. And there's much better imagery than what I will show you still to come. So let's go to the next slide. Okay, this is the reminder that the larger lobe is Ultima and the smaller lobe is nicknamed Thule for reference purposes. And then I think with that we can go forward. Yeah, this is an approach movie, and you can see the spin axis is basically aligned only about 30 degrees off our approach angle, and the end result of that is that there wasn't much light curve to be found, which explains both the Hubble and the onboard approach image results that couldn't get us a light curve in a period. But we were very lucky because this geometry actually gives us some views of the object broadside, so we get the most amount of real estate. And it also presents a puzzle to the object's accretion because the obliquity is very high, essentially normal to the plane of the solar system. And so the theorists are going to have to work on how you get to a state like that. I won't speculate here. The period that we did determine is 15.9 hours with a very small error bar. And I think with that, I will now go on. Just to say that the data that we have on the ground so far have not yielded detections of a coma or atmosphere, rings, any heliospheric interaction with the solar wind, and no evidence for satellites down to scale to about 1 to 2 kilometers, except in one region, intermediate distance from the target where we don't have the right data on the ground yet to have that smaller limit. If anybody wants to ask questions about the coma, rings, or heliospheric interaction upper limits, I can give you numbers in the Q&A. Next slide. Color. So here we have 3 images at about 240 meter per pixel resolution. Excuse me, the color is less than that. The color is at closer to 1 kilometer per pixel. But there you see the color on the left, the 240 meter per pixel panchromatic, and then the color draped over the panchromatic on the right. But please concentrate on the image on the left. You can tell that although there are albedo variations, that there's very little color variation. And we have now done a fairly good first order job of quantifying that. The 2 lobes have identical colors to within the error bars, which is in fact what's predicted from some Pebble collapse models. We do not see strong color variations anywhere across the 2 lobes. We do see some very subtle variations, particularly in bright spots, such as the 2 bright spots in the Thule or smaller lobe and at the neck. But those are only very small color variations, just a little bit above the error bars detected at about the 2 signal level. So this is a very uniform object, at least as seen in this early color data. Next slide, please. Just quantify that, show you the filter band colors of the 2 lobes, as well as the spots in the neck region, and then you can see the infrared reflectance spectrum of the object, which flattens out some from the red color slope of the in the visible. And then you can see a comparison to Pholus and a KBO 2002 VE95 there, which are quite reminiscent, even in terms of some of the absorption features. So I'm not going to say any more about composition unless there are questions. We're writing a paper for Science, and we'll say more about it there, and also at the Planetary Science Conference. Next slide. I'm going to end with a few higher resolution images of the spectacular object. This is the best resolution image that we have on the ground so far. It's also made at a higher phase angle and with higher signal to noise than the other images that I just showed off. So obviously it's a much richer data set, which we are mining as we speak. If we can go to the next one, it's an animated GIF that just shows you a small fraction of rotation between the lower resolution image and this one, just to give you a feeling for which things on the surface are real and how much better they sharpen up. Our actual highest resolution data set is going to come down in February at about 30 or 35 meters per pixel, which is between 4 and 5 times better than the better of these 2 images, and made at a steeper phase angle, closer to closest approach. And so we should see a much more terrain shadow, and that's all the good news. That phase angle is serving the noise will be a little bit less, somewhat less than we see here and here. But although these images are sufficient to trajectory from the space size flyby from bootstrapping away from images like these, where we compare the position of the target to where it's expected to be, tell us that with high confidence we expect that high resolution data set, which was made as a stretch goal. It was really made at risk for a number of technical reasons that we might not be able to actually get the target in the field of view when we were that close, or get all of the target. It looks like that's going to turn out pretty well. We'll see when we get the data down in a little less than 4 weeks. But we have very high hopes that the 35-meter class resolution imagery is going to be available to us in time to talk about it at the Planetary Science Conference. Next slide. I've only got a couple more. One of the things, there's many things that we could talk about in this image, but my time is limited, and I'm really about at the end of it. There's a lot going on in the geology here. There are lots of holes in the ground, and we can have discussions about which might be due to impacts and which might be due to other processes like sublimation or collapse pits, etc. But I want to point or show you these interesting mound-type regions that are pointed at by these 5 blue arrows. There are actually more than 5, but I didn't want to over-clutter. Each is bounded by some kind of a higher albedo border, and interestingly, they are all of similar surface area. Whether this is due to accretional subunits, or whether there was some thermal effect, for example, that happened, or something else that's an evolutionary effect that took place after Thule, I said it wrong, Ultima came together, we don't know. We do not see the same types of features yet on the smaller lobe, Thule, but with better data coming, we'll say more definitive things in about a month. But this is just a fascinating object, and there's a lot of work to be done here. We're going to be reporting on it at LPSC with about 40 talks on New Horizons science. And I can go to the next slide. which is just to continue on that. Also say that we have 2 special issues of Science. The first should be out in May or June, depending upon how long it takes to get the paper refereed. It's going to be submitted 3rd week of February. It's already in the 0th order draft form. There's another special issue that'll be out in August. And then we have a Icarus special issue that will come out next year with a due date of September 15th, in which we expect to have a very large number of papers, including some on the Pluto system and on observations of other Kuiper Belt objects made by New Horizons in that context survey that I spoke about. The abstract that's shown there just below is my own for the review talk that I'll be giving. All of these abstracts were turned in only about a week after the flyby. And as I said, there are about 40 of them by our team. So obviously there's a special session. There are also some papers that are going to be in poster sessions and some that are in Kuiper Belt sessions, particularly observations of other Kuiper Belt objects. But the vast majority of the 40 papers are about Ultima Thule and covering every aspect of it. When you read the abstracts as they go online here very shortly, you'll see that they're very preliminary. Most of them are more than a promise note. They do have results, but they all speak to the fact that by March, the talks are going to have a lot more meat to them than we could deliver with only a handful of images and spectra on the ground at the beginning of January. So I think with that, I'll just wrap it up and thank you for your attention. And if we have time, I'll take questions.
What? Okay, so Alan, can you hear me?
I can hear you, definitely, Tim.
Okay, good. So do we have questions for Alan? We have questions online for Alan.
I can read Dan. Would you like me to answer Dan Manzanek's question?
Sorry, Alan, we didn't hear you.
Oh, do you want to repeat questions to me? I see one that's online. It's just typed out.
I can just read the question online for everyone in the room. Any comments about the crater distribution? It looks like several small craters are just coming into view in the high-resolution image shown.
Yeah, can we go back? I think it's about 3 slides to that high-resolution 30-degree phase image. Not the animated GIF, but the slide just before that.
Is this the image you were looking for?
It's showing.
I'm not seeing anything. I just see
nothing's been shown online. We might not be able to show in our ever-growing IT.
Let me just assume you're on the right image. If you are, then you can see near the Terminator a series of holes in the ground. I would caution against calling those craters. You'll notice that they're all very similar in size and very close to one another. People more expert than I on the team are debating whether they might, for example, be collapse pit. The only depression or hole in the ground that we're confidently pointing to as likely to be an impact structure at this time is the very large divot in the smaller lobe we call Thule. We nickname that feature Tor. I don't have the ability to put a pointer on it, but it's upper right and pretty obvious on the smaller lobe. When we get the next and the highest resolution imaging data set, it's made at about, if I recall, about 50 or 55 degrees phase, we'll have a much better lighting geometry for trying to distinguish which features that are depressions like those on the Terminator are likely to be craters versus something indigenic. And of course, we're very interested in that for a number of reasons, including understanding the impactor population in the Kuiper Belt, and particularly the impactor population on classicals. So stay tuned.
And we have another question.
Regarding, this is Dan Adamo from Salem.
Hi.
Regarding the concentric rings on Thule, can you comment on their nature?
I don't know if you could hear that, but regarding the concentric rings on Thule, can you comment on those?
On the smaller lobe?
On Ultima, on the larger one.
Okay, yeah. Again, I wish I could use a pointer to make sure we're talking about the same thing. If we could go forward one slide, I want to verify, whoops, maybe one more slide. The objects, you mean the rings around these mounds that are pointed to by the arrows, is that correct?
Yes.
Yeah, there's a lot of debate going on about that. The albedos of those higher, of those so-called rings, as you're referring to them, are up around 15%. The average for the body is 8 or 9% in terms of I over F. Because our limited stereo already tells us that the features themselves that I'm calling mounds are topographic highs. It looks like the boundaries between them are topographic lows. Could that be caused by space weathering? Could that be caused by volatile accumulation in areas that might be coal traps? Could it be due to something else related to the formation of the mounds? We don't know, but those kinds of ideas are being kicked around.
Any other questions? And Meg?
I should point out, if I can just take 10 seconds, that this structure at the interface, the neck region between Ultima and Thule, is just remarkable. It is very symmetric, a bright ring right at the interface, and there are lots of ideas for how that may have come to be, both endogenic and exogenic. We're going to get a much better look at that, I hope, in the high-resolution data set to come down in the latter part of February. And we're also going to have an opportunity to look at to put compositional pixels on it in the infrared mapping spectrometer, and of course see it at a better color resolution as well.
Alan, one last question online. Any comments on the ratio of ice to dust?
Well, we can't measure mass, if it follows comets, it's probably primarily refractories with some amount of volatiles. Most likely, the extreme volatiles have sublimated away from the surface, else we would see a coma. As to the water content fraction, I don't want to speak to that yet, but I'm pretty confident that we'll be able to do that at LPSC.
Yeah.
You know, in terms of the surface, but not the interior, not the bulk body.
One last question in the room.
Meg Johnson. Alan, you talked about there's lots of power left in the spacecraft and it's all healthy. And what would be the ways you would find another target to fly to? Is it ground-based? Would it be just with using RORI imaging? Can you just speculate a little bit of what things you will think about to maybe try out to get another flyby target after MU69? Yeah,
we have some ideas. We need to do some work. Before the flyby, a lot of people wanted to work on that, and I really had to frown on it so we would concentrate on getting the flyby right, and that worked out. So we haven't yet begun to really do that. Ground-based is going to be very hard with current assets. In fact, really, we had to use the Hubble in order to even find Ultima and to track it. And things that are still further out are going to be even tougher because of the art of fourth decrease in brightness. I think the most likely technique that's going to be an important capability is using our own onboard LORI imager that can go down to 21st, and maybe we're going to do some tests later this year to 22nd magnitude to do a searchlight type search in front of us and detect targets that are immediately ahead of us giving us a matter of a few months of warning to target and then to do the intercept and the flyby. We really have to put a pencil to paper and very carefully work through the numbers. Kuiper belt extends out to about 70 astronomical units, but the number densities decrease, and so we really have to put the very best models against spacecraft and ground-based and Hubble capabilities over the next year or so before we start writing that extended mission proposal and find out just what we can do and what we can expect to achieve. I will tell you that there's more hydrazine in the tank right now after the flyby than it took to do this flyby, to target it and then to carry it out. So we're in good shape on that. We just need to take a look at the various search strategies and see which one is best.
Okay, thanks very much, Alan.
Thanks, Tim. I appreciate it.
Okay, so next up we have